In this module, we will use simple analogies to exemplify the concepts of statistical thermodynamics, such as microstates and configurations. We will illustrate how statistical methods can be applied to estimate entropy for large systems. Let's consider a simple example, a system of 10 indistinguishable coins. We will generate possible states of this system by randomly flipping the coins. In this setup, each specific arrangement of heads and tails for coins 1 through 10 is a microstate. Here are some examples of such microstates. On the other hand, if we count the total number of heads and tails without considering their sequence, we obtain a configuration. The weight of each configuration is the number of microstates corresponding to that configuration. As the first example, we consider configuration 1, where we have exactly 2 heads and 8 tails in our system of 10 coins. Some examples of corresponding microstates with different possible arrangements of coins are displayed here. Each unique arrangement is a distinct microstate, but they all belong to the same configuration because the total number of heads and tails is the same. The total number of microstates W corresponding to this configuration can be calculated using the combinatorial formula. W equals 10 factorial divided by 2 factorial times 8 factorial, which gives us 45. This means there are 45 possible ways to arrange 2 heads and 8 tails in different sequences. Now let's look at configuration 2, where we have exactly 5 heads and 5 tails in a system of 10 coins. Here you can see examples of different possible arrangements of coins, which correspond to the system's microstates in statistical thermodynamics. The total number of microstates W corresponding to this configuration can be calculated using the same combinatorial formula. W equals 10 factorial divided by 5 factorial times 5 factorial, which results in 252. This means there are 252 distinct arrangements of 5 heads and 5 tails. As you can see, the number of microstates is much higher here than for the previous configuration with 2 heads. This larger number of microstates indicates, as expected, that the configuration with 5 heads is more probable than the one with 2 heads. Let's now scale up to a much larger system where the total number of coins denoted by n equals 10 to the power of 23. This number is somewhat smaller than the number of molecules in 1 mole of a substance. In this scenario, we still consider a binary outcome, heads or tails, just like before. As an illustration, this image shows randomly flipped and placed coins. Their total number is only 1000, but the image already looks crowded. For a large system of n coins, each with a 50% chance of showing heads or tails, the most probable or dominant configuration is the one with an equal number of heads and tails. The number of distinct arrangements or microstates for this configuration can be calculated as the number of possible ways to distribute heads and tails equally among the coins. However, for a system as large as n equal to 10 to the power of 23, the resulting number of microstates or weight is astronomically high. This massive number of microstates highlights how dominant configurations become overwhelmingly probable in such large systems. When dealing with large numbers, calculating factorials directly becomes impractical. Fortunately, when calculating the entropy, we don't need to know the exact value of W, but only the natural logarithm of it. To simplify the calculations of factorial for large values of the argument, we can use Stirling's approximation. The natural logarithm of n factorial is approximately equal to n times the natural logarithm of n minus n. Stirling's approximation provides a good estimate for the logarithm of the factorials for large numbers. Using Stirling's approximation, we can find the natural logarithm of the number of microstates W for a configuration with equal numbers of two states, such as half-heads and half-tails. We start with the formula for the number of microstates, as shown before. The natural logarithm of W is equal to the natural logarithm of n factorial divided by the product of n divided by 2 factorial times n divided by 2 factorial. We can separate this into three logarithmic terms: the natural logarithm of n factorial minus the natural logarithm of n divided by 2 factorial minus another natural logarithm of n divided by 2 factorial. Next, we apply Stirling's approximation for each factorial. The natural logarithm of n factorial is approximately equal to n times the natural logarithm of n minus n. Similarly, each natural logarithm of n divided by 2 factorial is approximately equal to n divided by 2 times the natural logarithm of n divided by 2 minus n divided by 2. Thus, we have n times the natural logarithm of n minus n times the natural logarithm of n divided by 2 plus n. Next, notice that the positive and negative n terms cancel out. We can rewrite this expression as n times the natural logarithm of n minus n times the expression natural logarithm of n minus the natural logarithm of 2. Simplifying further, we see that the terms n times the natural logarithm of n cancel out, leaving n times the natural logarithm of 2. Thus, we have shown that the natural logarithm of the number of microstates W is equal to n times the natural logarithm of 2. Now we can apply the Boltzmann formula entropy S equals Boltzmann constant Kb times the natural logarithm of W. Substituting the values, we derive the following expression for the entropy of a system with n particles, which can be in two states with equal probability. S equals Kb multiplied by n and multiplied by the natural logarithm of 2. Evaluated for n equal to 10 to the power of 23, this results in a value of 0.957 joule per Kelvin. This example shows how we can estimate the entropy of a large system using statistical methods and approximations. It highlights the power of statistical thermodynamics in calculating thermodynamic properties for systems with an enormous number of particles.